Hi, in this video, we want to take a look at the clusters that we use in parallel programming in R. All right, so how parallel works for this is that it actually uses other packages to create the clusters. Remember that when I'm doing parallel programming in R, what's going on is that I have a bunch of work to get done, and I'm going to give chunks to different codes or different cores on my machine. And before I can do this work, I have to establish who's going to do each of these chunks? Who's going to do each bit of work? Well, the clusters are the workers in the situation. So the major hitters for the parallel package are Snow, Multicore, and RMPI. There are other packages available, but these are the big ones. All right, so Snow, this uses a message passing method. It can be used on both distributed memory or shared memory systems. That's it. That's advantageous if you're going to be working with with a more complicated computing situation. This works on most operating systems. It's independent of the operating system, and it works on Windows. And this is the one that for work, this is the one I usually use. Multicore, this uses shared memory. It can only be used on single multi-core machines. Now it runs on OS X and Linux. It does not run on Windows, unfortunately. Something that's nice about this is that you get additional functions to work with, the MC functions of MCLapply, MCMapply, MCmap. These all use the multi-core package. There's also RMPI. This uses a message passing interface. And this can be a good choice if it's available on your machine. I couldn't get it to run on my machine. My internet research was that other people have the same experience with Windows. So I don't know anything about it, but I know it's a major hitter. It's common, but I'm not going to actually run an example on that one. Okay, so when we go through and we declare our clusters, we get to just declare which type of cluster we're going to do. All right, there's two major types. There's PSOC, and then there's fork. All right, PSOC is the default one, and this is the one that uses the Snow package. All right, what this does is that this basically inside each core, it creates a new work environment. It's brand new, fresh, it's got that fresh core smell aspect. Well, so that's nice that, basically we're starting with a nice clean environment. A disadvantage of that is that anything that I have established in my workspace, in my main work environment, I have to manually pass that into each of the cores, which may be good, may be bad, depending on what's going on. If you have a large project and you have a lot of stuff in your workspace, it's good to not be copying a bunch of crap that you're not going to use into each core, because that will slow you down. But if I have a nice clean workspace and everything in there, or virtually everything in there, I want picked up by the cores, then I have to go through the additional step of passing information. So this is the default cluster type when I use the parallel package. It works on most operating systems, including Windows. This works well on my home machine and on my work machine. It starts with an empty working environment, and you have to pass objects that you want to be working with into the cluster. Now, this isn't the case if it's going to be generated by the clusters, like if we're doing random number generation, but anything like if I was going to work with the ISIS data set, I would want to actually pass it in manually. All right, so how we go about it is that when I make my cluster, I just set type equal to PSOC. And as always, we specify the number of cores that we're going to be using. In this example, I always put down 2 just to keep it simple and keep this fast. But on your machine, you would probably go the number of cores minus 1, more than likely, or the number of cores you have if you're going to dedicate the computer completely to the operation. Now, in each one of these code chunks, I'm stopping the cluster. The reason why I do that is I want to emphasize that that's good practice. We don't want to leave clusters floating around. If it's not being used, it needs to be shut down, and that way everything is cleaned out, and I'm ready to use it again for the next project. Now, fork, unfortunately, this does not work in Windows. what this does, this takes the work environment that you have and it copies and pastes that into each individual core. So this decreases the communications that you need to do between master and worker. But this is good because you don't have to do the communication. But if you're working on a big project and you only want some items going to the cores, this can slow you down. If I have like a bunch of large memory objects that are in my workspace and I start using forks for my clusters, then all those large memory items go over into the cluster and this can slow things down. Now, if everything's nice and clean, I don't have any junk around, then it's not an issue. Now, this example was not ran, but here's the code as I would write it. I'm using a Windows machine, so I can't run this example at all. Now, MPI is another option that we have, and it uses the RMPI package, and we declare that by going MPI like this. But on my machine, I couldn't get it to run, but this is how I would write the code. Unfortunately, there's just individual aspects of different machines, different operating systems that can block us from using certain techniques. All right, so now that we know like the different options when it comes to making the cluster, let's go ahead and like look at one. So what we're going to do, I'm going to, once again, I'm going to make a cluster. It's going to be PSOC. So remember, this is the default setting. So I actually could skip this line of code completely, but I want to emphasize what I'm doing so that it's easier for you to understand. And now let's go ahead and use the structure function to look at our clusters to see what are these, what do they look like, what's going on. All right, so I've got two of them, and we can see that the structure is going to be a list of two, which is going to correspond to each of the nodes. And so each of these clusters is stored as a list of 3 items. We have con, so we have sock connection, so, and then it's integer 4. We have host, and we have rank. When we get down to the next one, we see that the sock connection is 5. It's once again local host, and this time the rank is 2. And then for our attributes, this list is a sock cluster, and it's also called a cluster. Now, if I look at the type of the object of our clusters, it's actually a list, which is interesting. The length of the list corresponds to each core that we're using in the parallel programming. And then if I look at the type of the objects I have for each of the 2 lists, I can see that it's once again a list. And using the standard notation, so if I scroll up here, you'll notice I have a $ of rank. So if I go to the second item, I use $rank, I can call the object in the list, and we can see that it's 2. Now, if I want to get the IDs, so each time you do a cluster call, every time you create a cluster, it's going to have an ID. And so this enables me to go and like track where things are done. If I keep track of this aspect, keep track of the IDs, this way I have like more feedback. I know what's going on. Now, something about these IDs is if I run this and then I run another session later, I can get the same IDs coming up during different sessions. Now, in one individual session, the IDs will be unique, so it's not an issue if I'm trying to backtrack. But if I do multiple sessions, the IDs can be repeated. So that's something to be mindful of. And then we stop cluster. Okay, so something about using parallel programming in R is that there's going to be like a lot of communication going on, and I want control over how this happens. So something I will probably want to do is I'll want to initialize any object in whether that's data or library or setting options or running a function, something like that inside each node. I want control of it. I don't want to, I may or may not want to be automated. Well, so if I'm in the pstock situation, then I know that all the data that I have to work with is not automatically being carried over into the cluster. So I need to manually go in and get that data in there. So when I initialize, I'm going to need to initialize all the data that's not generated by a node. Any libraries, any packages I want to use, I need to get active. And then any global functions, such as options that I want to use within a node, I need to manually call each time within the nodes. Well, how do we do this? Well, what we do, we use these three functions to do it. We use cluster call, we use cluster eval queue, and then we use cluster export. All right, so cluster call is in a sense kind of like lapply, sapply, the apply functions, in that I specify which clusters I'm interested in, which function to run, and it runs that function within each cluster, as long as that makes sense. It won't throw an error. Now, cluster eval queue, what this does is I create an expression, some code that I want to have ran inside each cluster, and the cluster eval queue function will go through and execute that expression within each cluster. And then the cluster export, what this is used for is that I go into my main workspace, I find an object that I want within my primary workspace, and then the cluster export function carries that over to each individual cluster for me, which is nice. And so if there's a data set that I want inside cluster X, or if there's a data set that's in my main workspace that I want inside each cluster, cluster export will do this for me nicely. So cluster call calls a function with identical arguments on each node. So for this example, one thing I'm going to do, I'm going to go through, I'm going to load some part of the Philosopher's Stone from the Harry Potter books, from the Harry Potter package in R. Okay, so I make my cluster, and I look here. I'm going to do cluster call. I specify which clusters need to be this needs to be invoked on. Now, cluster call applies a function. Remember that this is important. It applies a function on each node. So if I want data, if I want to use this for passing data, this isn't the way I really want to do it, but I want to do something that's parallel in each of these three cases. Well, so what I did, I made a custom function, and I'm calling data, and then I'm going to print the first 17 characters of the first line of the first chapter of Philosopher's Stone. And by doing this, we can see that the very first part of the entire Harry Potter series is the boy who lived. And I'm just printing the substring on each node. Now, after I've done this, the entire book is actually loaded into each cluster. All I'm doing is printing this part just to convince you, the audience, that it's doing what we intended to do. So it's just at this point in the function call, the Philosopher's Stone, all the text from the book is in each cluster that I have. And to verify that it did what I wanted, I just pull the boy who lived from each of the books. This way I get some feedback to make sure it did what I intended it to do. And then, of course, I stop my cluster. So cluster call executes a function on each cluster. Now, cluster eval, what this does, this executes this evaluates a code expression that I write. And so here is my cluster eval queue. There's the cluster I want to run in. Now here, I've got expression, and you'll notice I have curly braces. Everything within the curly braces is what I want to have executed. So I'm saying load the Philosopher's Stone from the Harry Potter package, and then go ahead and grab the first 17 characters from the first chapter of the book. So let's see what happens. The boy who lived. All right. So either way, it will work. So if I just want to run one function one time, cluster call is the way to go. If I have something more complicated to run, and this is what I probably would be using more likely in a lot of situations at work, I'll be using the cluster eval queue. Now, cluster export, this one gets used a lot. And what this does is that this grabs an object from your workspace and it takes it and copies and pastes it into each one of your clusters. All right, so here, I'm loading the data into the main workspace. You notice that this is written just like I'm not doing any parallel programming at all. Now down here, I'm executing cluster export. I'm specifying which cluster I want to run on. And then I'm saying, these are the items I want copied and pasted into each cluster. And now, just to verify that it's doing what I want to do, I'm going to go ahead and print the first 17 characters within each cluster. And I can see once again, I get the boy who lived. All right, so when it comes to this aspect of parallel programming, we have two major options when it comes to the type of cluster, the PSOC and the fork. PSOC runs on Windows, fork does not. I know that people who are not Windows users hate Windows, but whatever. So in PSOC, nothing is copied and pasted into each of the clusters. That may be good, that may be bad, depending on what you're doing. Within fork, which uses multi-core, what happens, everything that's in my workspace gets copied and pasted into each cluster. That could be good, could be bad. And then we have three ways of initializing what's going on inside each cluster. Cluster call runs a function on each cluster. Second, we have cluster eval queue, which runs a code expression within each cluster. And then cluster export exports an object in the main workspace to each cluster. All right, well, that's all I've got for you. Take care and goodbye.